Sorry, I had to make a note for myself who's doing what. So, again, I'm not gonna draw the equipment diagram because you already seen it, for auto cycle, diesel cycle, they all look the same anyway. So I'm gonna, we need to have the PV diagram anyway. Process 2 to 3 constant pressure, process 4 to 1 is constant volume, and this is where we are constant entropy or isentropic. That's our PV diagram. Now this project, again, you need to read the project very carefully to see what you have. This is an ideal, diesel cycle. It has a compression ratio of 18. So R of V is 18, which is V1 over V2. And a cutoff ratio of 2. That means T3 over T2 is equal to 2. Now, at the beginning of a compression, the working fluid has a temperature of 80 degrees Fahrenheit. We add 460 to make it 540 degrees Rankine. Please do not use any decimal point, just exactly 460. And the pressure is 14.7 psi. Now, one thing that they say is that V1, and you see that I put the big V because the unit tells me that it's 117 cubic inch. If this was cubic inch per pound, this would be a small v. So now that I have this, that will tell me that I need to find a mass flow rate, and everything that I do, it's not per unit mass anymore. I have to make it a big Q, big W, and so on and so forth. Those are the hints that are hidden in the problem, and you need to pay attention. That's why I ask you to read the problem carefully. Now, what they're asking us to do is for part A, finding a T2 and P2. Part B, they want us to find the thermal efficiency and part C, they want us to find MEP, which is equal to the network divided by V1 minus V2. Now, if you look at this, I can also write the compression ratio as a big V1 over big V2. As you all know, big V is equal to mass times small v. Since the mass is constant, so V1 over V2 is just small V1 over V2, same thing. So just want you to be aware of that. Now, I can very quickly find the mass flow rate through this because V1 is equal to mass times R T1. I have the pressure, I have the temperature. This is universal gas constant. V1 is given. The only unknown here is the mass flow rate. So if I put 540 here, 14.7 psi, 117, cubic inch, and the value of R. I wrote it somewhere. I had to go and find it. The universal gas constant here is 0.3704. PSIA cubic feet on mass degree Rankine. That's a unit for it. So if I plug everything in, and of course, because of this cubic feet, I need to multiply the whole thing. So if I write 14.7 PSIA times 117 cubic inch is equal to mass times 0.3704 with that unit times 540 degrees Rankine. I need to have a correction factor in order to make it 17 cubic inch. That will take care of that cubic feet there. Now, if I look at here, this cubic inch and cubic inch is going to go. And then this degree Rankine is going to go with this degree Rankine. The PSIA is going to go with that. It's going to be gone because of that. So the only thing that I have left as far as a unit concerned is pound mass. And that's what I'm looking for. So if I do that, the mass flow rate of air is going to be 0.005 pound mass. Any questions? This correction factors in your textbook, the value of R is in your textbook for the English unit. Now I found the mass. So one thing on the given part that I missed is that this is very important how to read the problem carefully. In this problem, they say assume cool temperature. What does it mean? We know that Cp and Cv are constant, are a function of the temperature. As the temperature goes up or go down, they change. But if I assume throughout my cycle, it's a cool temperature, they indirectly tell me that Cp and Cv are constant. So Cp and Cv are constant. I make my life much easier so I don't have to go through the table. Again, please read the problem carefully. So when it says utilizing the cool air standard, assumptions, the cool air standard assumptions means Cp and Cv constant. That's one of the tricks. Sometimes it's utilizing room temperature or utilizing temperature remain at 300 degrees Kelvin. All of that means Cp and Cv are constant. Since that's the case, now I look at, I have a T1, so I need to find a T2. T2 over T1 is equal to V1 over V2 to the power of K minus 1. This is given 18. T1 is given 540. So all I need to do find the value of T2. The value of T2 becomes 1716 degree ranking. That's portion of the part A. Then they ask, find the pressure. Well, I know that P1, V1 over T1 is equal to P2, V2 over T2. So I have T2, I have T1, I have V1 over V2, and I have P1. I have only unknown is my P2. So from this relationship, I can find the value of P2 to be 841 PSIA. Now, another way of writing this, I can do it this way. This is again part of the ideal gas equation. And it says P2 over P1 is equal to V1 over V2 to the power of K. I can also do it this way, find the same answer. Either way, it's all ideal gas equation. This is for isentropic equations, T2 over T1, P2 over P1, all of that isentropic ideal gas equations. So I have T1 was given, I found T2, now I need to find T3. How can I find T3? R of C is equal to 2 and is equal to T3 over T2. So if I multiply T2 by 2, I will get T3. That would be, well, the 34, 32 degrees ranking. And finally, I can write T4 over T3 is equal to V3 over V4 to the power of K minus 1. And look at this again. We prove that this is the same as R of C over R of V. I have both of them. R of C is 2. This is 18. If I put it here, K is 1.4. So the only unknown is T4. From there, I can find the value of T4 to be 1425 degree ranking. So rather than going around the cycle and going through the table, finding H values and U values, in a matter of a couple of minutes, I found all the temperature. By the way, part A of a problem in a process is already solved. I found T2 and P2, both of them. Any questions so far?
I have a quick question.
Sure.
What did you say K equaled again?
K is equal to 1.4 for air. K is a constant. And as you know, K is equal to Cp divided by Cv when they are constant. And that's how we can find the value of K.
Okay, thank you.
No problem. Sometimes the problems say assume K is equal to 1.35. Then you have to just, instead of 1.4, put 1.35. But if nothing's said, K is 1.4 for air. Now, I went through everything and I found all my temperature and cycle. Now, the rest becomes much easier. So, my Qin is equal to mass of air times CP, why CP? Because it's a constant, pressure, times T3 minus T2. I have the CP value from the table. If you look at that value, CP is 0.240 BTU per pound mass degree Rankine. That's from the table. I have the mass flow that I've calculated. I have T3 and I have T2. So the value of my Q in becomes 2.051 BTU. Now I need to find the Q out. So if you don't mind, I'm going to erase that part. Now the Q out is equal to the mass this time times CV, because the process is as constant volume, times T4 minus T1. The value of CV is 0.171. Unit is a BTU per pound mass per degree Rankine. I found T4, T1 was given, I calculated the mass, so therefore my Q out simply becomes 0.754 BTU. I look at the thermal efficiency, part B. I plug these two numbers here. So my thermal efficiency, if I plug them here, I get a thermal efficiency of 63.2%. So now I have to worry about MEP. For MEP, I need to find the network. I know that the network is equal to Q in minus Q out. And this is big W. Now, if I plug the number in, my network would be 1.297 BTU. Now, I have V1 is given, and I know that V1 over V2 is 18. So if I divide 117 cubic inch by 18, I get the value of V2. So V1 over V2 is 18. In that case, would be 117 cubic inch divided by 18. That would give me V2. In that case, the value of V2 becomes 6.5 cubic inch. So now I'm looking at this, I got everything that I need. This would be the W net, which is 1.297 BTU, divided by 18 minus 6.5. The unit for that is cubic inch. Let me erase this part. Now, if I look at it, this is BTU, this is cubic inch. So there must be a correction factor in order to find MEP in PSI. This correction factor is basically 778.17 per 1 BTU. Or the unit for that is pound force This is my correction factor. You find it on your text, that I have to multiply it here in order to find the MEP. Now, once I do that, at the end, I will find my MEP to be 110 PSIA. So that's how you solve this problem. As you can see, it becomes very easy when you have a temperature and CP are constant. You don't have to go to the headaches of the table. If I wanted to do this and going back and forth on the table, probably would take us about half an hour or 25 minutes. But we did that very quickly, like 10 minutes. So that's the difference. That's why it's all depends on that huge assumption. Any questions on that? Okay.
I have a question.
Final
Professor?
problem, right? Yes.
What does the MEP equal in the bottom left?
The MEP is equal to net work divided by the difference between maximum volume and minimum volume. At the end, the value is 110 PSIA. Yes. Oh, I'm sorry. Thank you. Yeah, that's 117. I don't know, for some reason I put 18. Thank you. Any other questions? All right. Let's do another problem. Again, another example of diesel cycle. And let's see this time what we get, what do we have. Now, once again, air standard diesel cycle has a ratio, compression ratio, RV is 18.2. This one is V1 over V2. The air enters the compressor. That means T1 is equal to 120 degrees Fahrenheit. Again, plus 460, that will give me 580 degrees Fahrenheit. And of course, the pressure is atmospheric pressure, which is 14.7 PSIA. Considering the variable specific heats, what does it mean? That means CP and CV are not constant. So CP and CV are not constant. And they tell me at the end of a heat addition, 0.3, the temperature is 3,200 degrees Fahrenheit. Now, part A, find heat added to the system per unit mass. What does it mean? It means small QE. This is the amount of the heat added to the system right here per unit mass would be a small QE, which is equal to H3 minus H2. Part B, heat rejected. per unit mass. That means small Q out, which is U4 minus U1. And finally, part C, the thermal efficiency, which in this case would be 1 minus 1 Q out over Q in. So, because I don't have too much space, I'm gonna just take this out. And I'm gonna rewrite. I need to find the Q in, which is equal to H3 minus H2. I also have to find Q out, which is equal to U4 minus U1. Now, writing this equation helped me out that I know exactly the 4 parameters that I need to find. So I don't waste my time going around and finding a whole bunch of other things that I don't need. So since the CP and CV are not constant, that means I gotta go to the table. Now, for those of you that's supposed to have your textbook with you, now I want you to go to table A17E or English unit. So at a state 1, at 580 degrees ranking, I go to table 17, A17E, sorry, and I find the value of U1 and VR1. Can anybody tell me what these values are? Anyone? I don't need it. BTU per pound mass. What is the value of VR1? Perfect. Thank you so much. Please bring your textbook. You're not helping yourself if you don't have it handy, because this, I'm doing all these exercises for your benefit. I could have just gone through it and get to the next topics. If you don't take advantage of this opportunity and learn, you're going to have a problem with taking a test. So now, at a state 2, I'm going to write V1 over V2 is the same as VR1 over VR2. Now, V1 over V2 is given, 18.2. VR1 is that, so very quickly I can find the VR2 to be 6.632. Now, at the value of VR2, I go back to table A17E. I need to interpolate, of course. What do I need? I need H2 and H3. So here I find H2 and T2. If you do that after the interpolation, you get 849.48 BTU per pound mass. So that's my first parameter. This is my second parameter. Temperature at point 2. Oh, I'm sorry, I made a mistake. That's 429.56. This is roughly 1725.8 degrees Frankie. I needed this temperature. Why? Because when I go to state 3, I need to find R of C, because I cannot solve a problem without cutoff ratio. Cutoff ratio is not given to me, but I know that it's equal to T3 over T2. T3 is given, T2, I just found it, so that my cutoff ratio value becomes 1.854 that I can use later. Now, at T3 equal to 3200 degrees ranking, I go to table A17E. This time I find H3 and VR3. Why H3? Because I need H, and this is at a constant pressure. I don't want to find a U value. If I do that, the H3 would be 849.48 BTU per pound mass. That's my third parameter. And the VR3 is 0.955. Check these values if you see these on your table, and if those are correct. Finally, at a state 4, I write VR3 over VR4 is the same as V3 over V4. We proved its value is equal to R of C over R of V. Now, I just found R of C. R of V was given. VR3 is right there, so the only unknown becomes VR4. So VR4, after the calculations, becomes 9.375. Now, once I found it, I go back to table A17E. This time, I find U4. Since they didn't ask me to find T4, so I'm not going to bother with it. I just want to find the things I need. In this case, the value of U4 would be 272.58 BTU per pound mass. For those of you who are interested to know this value, T4 would be 1531.8 degrees Rankine. So I went around the table, find all the 4 parameters that I need. So now I'm looking at this. I have H3 and H2, U4 and U. So my Qing, if I plug the number in, H3 and H2, my Qing becomes 419.9 BTU per pound mass. My Q out, if I deduct U4, I mean U1 from U4, I will get the value of 173.7 BTU per pound mass. Finally, well, this was part B. Finally, I need to find the value of thermal efficiency. I have Q out, I have Q in right in front of me. Plug it here, I get the thermal efficiency of 58.6%. That's part C of the problem. So again, please don't forget, under no circumstances, you want to take a degree Fahrenheit convert it to degree Celsius, and try to solve a problem. Once you do that, everything you do after that, it's all trash. You cannot do that. So please solve the problem in the system that you have, whether it's SI unit or English. So be very, very careful on that. Any questions on diesel cycle? You should now solve diesel cycle problem with your ice cores, right? Arthur, let's see, you still, no, this is crazy. We need to find out why you are not allowed to record. No problem. Let us know if there's anything I can do. Now, I'm going to give you something that you're going to see on your homework assignment. I don't want you to be surprised. Let's see. I give you a homework as an exercise, and that could be on your test also. And that is called man-made cycle. It's not a real cycle. It's not Carnot cycle. It's not Otto cycle. It's not diesel cycle. It's not a cycle that you're familiar with. It's a made up. The reason for that, for you to be able to practice, to develop TS and PV diagram based on whatever that man-made cycle is. Now, Arthur, give me a process. Let's say process 1 to 2. What do you want it to be? Isentropic. Okay. All right, Blake, give me a process 2 to 3.
Isochoric.
Isochoric? All right, let's see. Wow. Jack, give me a process of 3 to 1. Jack is, I guess he fell asleep. Abraham, give me a process of 3 to 1. It's an isobaric.
Yeah, I was gonna say isobaric.
Isobaric. So this is not a 4-point, it's a 3-point. They give you a process, they ask you to find or draw the TS/PV diagram. Let's see if we can do that. That's a TS, and that's a PV. So I look at 1 to 2, isentropic. 1, 2. 2 to 3, isochoric. So that's 2 and 3. That's where V2 is equal to V3. 3 going to 1 is at constant pressure. Constant pressure. So that's 1. So that's what I have. So now I need to complete this. My 1 and 2, how it's going to be this way or this way. Because 1 and 2 and going up, right? Isentropically. So that completes my PV diagram. Now, for 2 going to 3, I have to go isentropically up. Then, I mean not isentropic, exponentially up and exponentially down. So for some made up processes, this would be the TSM-PV diagram. So you can always come up with these. There will be an exercise on your homework assignment. I want you to pay attention to it and try to solve that and see if you can work that out. If you really can work that problem assignment and pay attention to it, then you know chapter 9. You know all the cycles, you know everything. That's how important this man-made cycle is. So be aware of that.
And Professor,
Yes.
just to harp back on something that you said previously when we were going over cycles. So for actual cycles, we would need 2 isentropic processes, correct?
Well, for actual cycle, all the compression and expansion are, isentropic. That's given. But in this case, for man-made, for instance, this could be work in or work out because it's isentropic. This could be Q in and this one Q out, for instance. We don't know. They usually, when you have a man-made, they will tell you process 1 to 2 isentropic heat addition, expansion. This one, they can say, isochoric heat addition or heat rejection. Sometimes they say 2 to 3 is heat addition, 3 to 1 is also heat addition. Whatever they say, it doesn't matter. At the end of the day, that would be TSM-PV diagram. But you're right. Every time we have an isentropic, it's either work in or work out. You cannot have an isentropic heat addition. That's not going to happen because isentropics are for compression and for expansion. Any questions on that? No, don't, please, don't stay focused on the practical part of it because this is not practical. This doesn't make any sense at all. We just made it up. I didn't make it up, you guys made it up. No, in real life, there is no such a thing. You don't have that in real life. Real life are those cycles that we discussed and we talk about. Those are the practical, except the Carnot cycle, which is the theory, the rest of them are practical. And as you notice, we had Otto cycle with a little bit less efficiency. Now we went to diesel cycle with a huge efficiency. So we can see how valuable the diesel cycle is. And that's why today we use diesel cycle, engines everywhere in any kind of a practice that we have, from the generator to backup generator or emergency generator, all the way to running the ship, running so many things that we can do with the diesel cycle. Trucks, bulldozers, forklift, you name it. Now, the final part of chapter 9 It's a Brayton cycle. Or, as known in industry, gas turbine. And the biggest example of that, of course, would be jet engine. Now, again, we will have a compressor. Air will enter in at point 1. Around at point 2. Into the combustion chamber. That's the fuel. Come on at point 3. Now this time, on this side, we have gas turbine. This is point 4, and that is exhaust. And of course, we're going clockwise as well. As you can see, the only difference here, we replace the engine with a gas turbine. Everything else stays the same. Now, we can put a heat exchanger to get back to point 1, or complete the exhaust and keep taking the fresh air. In case of a jet engine, there is no heat exchanger. We keep getting fresh air as we fly into. As you will see, although gas turbine will generate a lot of power, but it's the most inefficient cycle in chapter 9. By itself. Now, when we're using it for jet engine, we don't care about the power. What do we care? We care about the thrust, right? Because we want to keep the airplane up. So who cares that we don't generate efficient power? As long as we can generate enough thrust to keep the airplane up in the air and then fly from one point A to point B with 300-400 passengers. But as a power plant, it's not an efficient way of doing it by itself, unless we combine it with something else. In chapter 10, we're going to show you that we can combine these 2 chapters together, and all of a sudden this becomes a very efficient way of doing work. But for now, in chapter 9, we're going to stick with what we have. So as always, there are processes involved. Process 1 to 2 is given as entropy. That will never change. Process 2 to 3, it's isobaric heat addition. That's where P2 is equal to P1. Process 3 to 4, once again, there is no exception. It's always isentropic expansion. S3 is equal to S4. That's isentropic compression. 1 and 2 and 3 and 4 never changes. The only processes you can change 2 and 3 and 4 and 1. So 2 and 3 is isobaric. Now 4 Going back to one, once again, is isobaric heat rejection. Meaning P4 is equal to P1. As you can see, auto cycle, these two prices were the same. The auto put 2 and 3 and 4 and 1 in a constant volume. Diesel came along, changed this one only to constant pressure, kept that one at a constant volume. Now, Brayton cycle is saying we have 4 processes. 2 of them isentropic, 2 of them isobaric. Now, to do the TS diagram for that, I have point 1 going to 2, and then 3 to 4. That's my TS diagram. Very easy. Any questions? Of course, let's see, we usually show that at a dotted line because there is no equipment, we just exhaust. And point 3 is going to be much higher when we do it that way. Only point 3. So we still have work in, work out, here out, and here in.
Professor, quick question.
Yes,
On process 2 to 3, for the heat addition, should that be P2 is equal to P3?
yeah, it is.
Oh, sorry.
See, this is not a PV diagram. This is a TS diagram.
I think
At point 3 is much higher at point 3.
On the processes above the graph, where it's next to heat addition, it says P2 equals P1.
P2 equal to, oh, I'm sorry. P2 is equal to P3, not P1. Thank you. So that is our TS diagram. Now we want to look at PV diagram. Our PV diagram, they have process 2 and 3, constant pressure. They have process 4 and 1, constant pressure. P1 is equal to P4, P2 equal to P3. Now we're going to connect isentropic part, so we have a complete PV diagram. This is the PV, and that's the TS side. However, like diesel cycle, the TS diagram didn't help us out. In this case, the PV diagram is not going to help us out. So we never use this. We focus only on the TS diagram. So far, auto cycle, you need both diagrams. Diesel cycle, you need PV diagrams only. Now the gas turbine or Brayton cycle, you need only TS diagram. That's it. You don't need anything else. Any questions so far? No questions. Okay. I need to erase this equipment arrangement, which is the same thing you have seen before, The only difference, instead of engine, I put gas turbine. Now, let's talk about characteristics. Here we have pressure ratio, not compression ratio. And the pressure ratio is equal to maximum pressure divided by minimum pressure. And we show that as R of P. Now, we also have relative pressure at a given point. That means we have PR1, PR2, PR3, and PR4. For every one of these points, we have relative pressure. Similar to what we had before, the relationship with the compression ratio and the relative volume, we have the same relationship. That's P2 over P1 is equal to PR2 over PR1. P4 over P3 is the same as PR4 over PR3. Now, we know that P2 over P1 is R of P. What is P4 over P3? If you look at that PV diagram that I just erased, that's 1, 2, 3, and 4. P4 is equal to P1, right? So I can replace this with P1. P3 is equal to P2. That becomes P2. Now, looking at that, this is P1 over P2. That means PR4 over PR3 is the reverse of R of P. This one is reverse. In an auto cycle, we had the reverse. However, diesel cycle was different. We found out there's a cutoff ratio over R of P. We just solved 3 problems. So remember that, and of course, this is R of P, and this side is 1 over R. Now, going around the cycle, finding the quantities of various energy, our Q in is equal to H3 minus H2. Our Q out is equal to H4 minus H1. There is no constant volume here. So everything is delta H across the equipment. Work in is H2 minus H1. Work out is H3 minus H4. The difference between these two, Q in minus Q out, will give you the network. Also, the difference between these two, work out minus work in, also give you network. this we said never change, no matter what cycle you have. Doesn't matter how you find the Q in and Q out or work in and work out, the difference is never, that will never change. How about thermal efficiency? That never changes either. That becomes net work divided by Q in or 1 minus Q out over Q in. That will never change it. So this part of it, you have already worked so many examples, you know, that never changes. Finding these values, it's up to us. These are not equation. This is equation. This is equation. This is an equation. None of these are equations. These are the relationship that we built. Q in is a delta H cost the equipment. Q out delta H cost the equipment. That's how we look at it. We don't say H4 minus H1 is an equation. Because once you consider an equation, if the numbering changes, which you see later, then you get confused. You don't know what you're doing. So be very careful. There is one more characteristics. If you remember, both for auto cycle and diesel cycle, we had a mean effective pressure. Here, we have something called backwork ratio. So I usually say BWR. Your book shows it differently. By definition, the backwork ratio is the work of a compressor divided by work of a turbine. Why that is so important to know? When we want to run this cycle, this compressor already connected with the battery. We crank it. As soon as this starts, this will generate electricity. The electricity that is generated here come back and run the compressor. The reason this cycle is not that efficient because this ratio is high. Most of the power that we are generating used to run the compressor. Look at your car. When you start from your battery. The minute the engine will come out, there is a relay switch. We'll disconnect the battery and you are running all your electrical power through the alternator from the engine. At the same time, alternator keep charging your battery. This is the same concept. We bring a huge battery connected to the compressor, we crank it. Once it's done, we disconnect the battery, and from that point on, this power will help running this compressor. So the higher of this ratio, the biggest problem we're going to have with this cycle, that means the lower thermal efficiency. So that is a problem with this cycle. Once we start doing some examples, you find out. So the backwork ratio, which is unique for this cycle only, is the work of a compressor divided by work of a turbine. I'm going to leave it at that. I'm going to solve some examples to get the hang of it. Then, because of inefficiencies of this cycle, we're going to do a couple of things to it. It's called modification. modifying it to make it more efficient, increase the efficiency of the cycle. That's what we're going to do. Now it's a couple of minutes before our time. Do you have any question before we say goodbye and see you on Wednesday?
For the back work ratio, it's compression over turbine, or what's the T?
Work of a compressor divided by work of a turbine.
Okay, thank you.
This is work in divided by work out. From this point on, we're not going to call work in and work out. We call them work of a compressor, work of a turbine. This will change to WT. This will change to WC. Not that WC that you're thinking of. This is work of a compressor. Does anybody know what WC means? Guys, water closet, very good. The British use that for the restroom. So if you go to Britain and you're looking for a restroom, say, excuse me, where is the WC? That will point you to it. You say restroom, so you want to rest? What do you want to rest for? This is an airport, you can't rest here.